Hi everyone, it's time for the last topic of the semester, spherical and hyperbolic geometry. I introduced them briefly in class and I thought I'd make a short video explaining them a little bit better. Now again, this isn't going to be on your final, it's kind of an advanced topic, but it's a little fun and I'd encourage you to think about it a little bit. So, we're used to Euclidean geometry, where things are on a grid and we can move in the four cardinal directions, northeast, southwest, and it's kind of how we measure in everyday life, how everything's kind of on a grid. If we break out a ruler or a tape measure, we'll see it's flat, and if we were to measure with them, we'd get kind of measurements in a flat grid. Now, obviously, the world is not flat, it's a sphere. So let's take a look at how spherical geometry actually works. So I'll leave this over here because we'll deal with that later. We'll just think about an actual big sphere. And we could put a point on it. Let's put a couple points on it just for reference, and we can kind of rotate it around. Obviously, if you've ever lived on the Earth, we understand that we're living on the surface of a round planet, as long as you're not a flat earther. And basically, any point might actually have some slight curvature to it. It's kind of hard to show it. Well, we could see it like right here. See, there's a curve between these two lines. And if we were to look here, well, why don't we actually draw the segment? Click and drag. So we see there it kind of goes in a round hump almost. We see it's curved because we're traveling along the surface of the sphere. So spherical geometry is used more when we're dealing with things on the planet. And here's an interesting fact. So this is another sphere I have, and we can see here we have uh, a triangle here, and we have there are three different angles. But what we notice is that because I drew these with the great circles, which are circles that extend all the way through with a diameter the same as the diameter of the sphere. All the angles would be 90 degrees in this case. Let's rotate that around. So we see the triangle. It's obviously a little distorted. It almost looks like it's exploding from the outward. And we get a round triangle with up to three 90-degree angles just because of the way spherical geometry works. Because we're traveling on the outside of a sphere, we kind of just have more distance to cover almost. That lets us have these wider angles. We use this a lot when for flying planes, for traveling in large ocean voyages, things like that. Now, the other type of geometry that's kind of burgeoning is hyperbolic geometry. So here's like an approximation of the hyperbolic plane. One thing to keep in mind, while these triangles in the center are visually bigger, they technically have the same area as the ones all the way on the outside, just because of the way the plane works. And we wind up getting curved lines. So technically this curved line is actually straight because it's drawn just from point to point. See, these go across the plane and it is more straight. Let's actually take a look at a tool that'll let us experiment with it. So this is just a pre-drawn thing that they give us. They draw a circle which seems to be increasing and decreasing with size depending on where we put the center. And if we look over here, it actually has the lengths of the measurements of each of these segments. So from A to O and from A to H or A to P, I, M, all these segments are the same 1.3 units long. And that's despite these looking very short. And that's because of that fact that I showed you earlier that, see, these are smaller areas. Well, obviously, that have smaller dimensions in general to have what looks like smaller areas despite being the same area. Or you perceive them to have smaller dimensions despite them being actually the same length on this disk. This is kind of like traveling on, say, the inside of the Earth. Uh, and it's actually used a lot with space travel. It's kind of foreign because we're not trained to think in that manner. Now, let's let's just experiment a little bit with this. I'll plot a few points, A, B, and C, and I'll construct segments between them. Go away, D. Okay. How about this? And we see that these points, depending on where we put them, the angles actually get very strange and very shallow. Let's measure those. What do we know about triangles? That's right, they have 180 degrees. Well, let's look at the sum of this triangle. It has less than 180 degrees. So that postulate that we've always held true, the fact that all triangles have 180 degrees isn't quite true in this geometry. And that's kind of like what we showed you in the spherical geometry where a triangle had 3 right angles. So essentially, we see that the differences are they they don't really. Oh, I think my app crashed, unfortunately. They don't really follow. Here we go. They don't really follow the same rules that you might expect them to in regular Euclidean geometry. If you'd like, there's a video explaining some of the actual formulas behind some of this that I've left up on the PDF that I'll upload tonight with all of this information. And you can also experiment with these tools on your own if you'd like to. All right, I hope everyone has a nice break. Thank you.